So a point source solution, or a fundamental solution, is a solution of a PDE which at time 0 is a Dirac delta. And if the solution also satisfies given boundary conditions, then it's called a Green's function for the initial boundary value problem. The reason that these kind of functions are important is because they allow you to solve PDEs with arbitrary non-homogeneous term. So there's sort of a minor miracle that occurs. Once you have a fundamental solution or a Green's function, then if somebody gives you an arbitrary forcing term, a non-homogeneous term, you can just integrate the solution you have against it. It's called convolution, and it will instantly produce a solution for the non-homogeneous problem. So we'll look at that kind of thing later. For now, I'm just going to give you some examples of fundamental solutions for the heat equation and associated PDEs on R and R2. So if we look on the line, the fundamental solution for the standard heat equation is given by G of x mu t, where G of x mu t is this normal distribution character that we found in the previous video. Okay, and so the reason for the G there is because it's named after Green. Okay, and so if we look at an advection diffusion equation, so let's see, minus cux, then the corresponding fundamental solution can be found by just looking at how G behaves when it's slid, translated to the side. So you just make that substitution, x goes to x minus ct, so that it's got that constant motion at speed c built into it. Then if we look at a diffusion growth equation or a diffusion decay equation, so let's tack on a gamma u term right here. Then the solution is going to be e to the gamma t gx mu t. Okay, so if you go back to the form over here, then that means that there's going to be some gamma t term tacked on there at the end. Okay, if we look on R2 and we suppose that we have radial symmetry, so I'm going to drop some point source of heat down at the origin and then let it propagate outwards. So we'll let r be the radius, that is the distance to the origin in R2. And so then the PDE that we're looking at is going to be ut is d times 1 over r u sub r with respect to r. And then the solution is going to be given by 1 over 4 pi dt without a square root, e to the minus r squared over 4 dt. So you can see the role of the spatial rescaling and how that's determined by the coefficient out front. Similarly, in R3, if we have spherical symmetry, and so now to indicate that it's spherical, we'll let rho be the distance to the origin for spherical coordinates. Then the differential equation for heat ends up being d times 1 over rho cubed times rho squared u d rho with respect to rho. And the corresponding solution to the heat equation is going to be 4 pi dt to the minus 3 halves times e to the minus rho squared over 4 dt. So the basic rule that you have here for these is that you've got 4 pi dt square rooted raised to the power of the dimension of the space that you're working in.